Today we're on to learning target number 13, calculating the nth root of a complex number, which, if you've been paying attention to your learning target list, is the last of the Unit 10 learning targets. So today's focus is going to be on roots of complex numbers. This is coming after we did the powers of complex numbers yesterday. Okay, first off, just a little definition of the nth root of a number. So a complex number, v, which would be in standard form, a plus bi, is the nth root of z if v to the n equals z. Because if you were to solve that equation by taking the nth root of each side, then v would equal the nth root of z. Okay, so what we're looking for are numbers v, the numbers v that would satisfy that nth root of any given complex number. Here's how the formula works. It's similar to de Moivre's in general form, but it just has one little extra quirk. So finding the nth root of a complex number, so you have your standard, your trig form of a complex number, r cosine theta plus I sine theta. If you want to find the complex numbers that are the roots of that, then you take the nth root of your r. So de Moivre's theorem said if you're taking it to a power, take the power of r. Now we're taking a root, so we're taking the root of r outside. That is a parallel here. And then you have cosine plus I sine still in parentheses. You take your angle, you divide by n this time. De Moivre's theorem had you multiplying by n for theta. So we have the nth root and the division by n that are the parallels to the de Moivre's theorem powers. When we're taking the roots, we're now rooting and dividing. The one difference here is that each angle, you're going to come up with various angles for your answers. So instead of having the same theta over n every time, you're going to have theta plus a multiple of 2 pi divided by n. So what it's saying is you're finding the coterminal angles. You're given theta, and then 2 pi later, and then 2 pi after that, and 2 pi after that. So it's all the coterminal angles that are going to help you find your roots. K starts off with 0. This is the trickiest part. So it starts off with 0, which means no multiple of 2 pi. So your original theta over n. Then k becomes 1, so I add 2 pi. Then k becomes 2, so I add 4 pi, and so on. And you go all the way up to n minus 1 roots. So let's say you have the 6th root. You're going to use k as 0, 1, 2, 3, 4, and 5. So you go up. Notice that since you're starting with 0, that's going to be your number. So if you go to the 6th root, you should have 6 answers, but you're going to start at 0. So 0, 1, 2, 3, 4, 5 is actually the 6 answers that you need for the 6th root. One little hint for you, when you're finding the nth roots, you need to make sure it's in trig form first. This formula is all about the trig form, just like de Moivre's theorem was. So if we have a complex number given in standard form, we're going to have to convert it before we do anything else. Okay, find the indicated roots of the complex number. Leave your answer in trig form. That's very generous, very nice that we don't have to redistribute. Find the 4th roots of z equals 5 cosine of pi over 3 plus I sine of pi over 3. So I'm going to use the formula here. The formula says if it's a 4th root, my n is 4. Okay, so I'm going to use 4th root of 5. Then I'm going to set up my middle part. Cosine pi over 3 plus 2 pi k all over my n, which was 4, plus I sine of the same angle. And that's going to be, for k equals, we start with 0, we need 4th roots, so we're going to go up to 3. 0, 1, 2, and 3. From here, there are various ways that you can do this, but I find it easiest to solve for that theta first and get a common denominator so that I can just quickly plug in the k's to come up with my angles. So I'm going to think about my theta as pi over 3 plus 2 pi k all over 4. And I'm going to flip that 4 to the top and multiply, so it becomes pi over 3 plus 2 pi k times 1/4 instead of dividing by 4. That's going to get me pi over 12 plus, and this will reduce to pi k over 2. Now I need a common denominator to be able to put them together, so I'm going to change this by multiplying by 6 on the top and the bottom. Pi over 12 plus 6 pi k all over 12. So what this is going to allow me to do is figure out, okay, if k was 0, and I'm going to kind of write it all out this time, but for most of you, you probably won't have to write it out. For k is 0, I'd have pi over 12 plus 6 pi times 0 over 12, which this is going to go away, so I have theta is pi over 12. For k equals 1, I plug in a 1. I get pi over 12 plus 6 pi times 1 over 12. 6 times 1 is 6, plus the 1 we already had. It's going to get us a theta of 7 pi over 12. Keep going. If k is 2, this time I'm doing pi over 12 plus 6 pi times 2 over 12, which is going to get me a theta. When I multiply by 2, I get 12. Add the 1 we already had. That's going to give me 13 pi over 12. And repeat for the last one. K is 3. Then my theta is going to be pi over 12 plus 6 pi times 3 over 12. So 18 plus the 1 we already had is going to give me 19 pi over 12. So I come up with my 4 angles. My r out front, once I've taken the 4th root, is going to remain the r. So I start taking the roots of this number. So my first root, we called this v up in the definition, so I'm going to call it v1. My first root is going to be that r, 4 through to 5, which if it simplified we would, but it doesn't. Cosine. Now I've simplified this fraction, and I know what the first one should be. It should be 1 pi over 12. So cosine of pi over 12 plus I sine of pi over 12. Then I go on to my second root, which is still the 4 through to 5, but this time my k would be 1, and I'd have 7 pi over 12. Cosine of 7 pi over 12 plus I sine of 7 pi over 12. And we repeat this with the other angles until we've listed out, if we've got the 4th roots, we need 4 answers total. Fourth and final root, cosine of 19 pi over 12 plus I sine of 19 pi over 12. And all 4 of these are your answers. So the 4th roots should have 4 answers, each with your rooted r and then the various angles you solved for when you plugged in k. What I want you to notice is when we found this common denominator up top, we said we were adding a multiply of 6 pi k over 12. Since our denominators were the same, what we were really just doing to the top was adding a 6. So if you kind of look down our list here, we have 1 pi over 12 as our original, the original pi over 12. Then we added 6, so 7, then add 6 again, 13. Then add 6 again, 19. So once you kind of get to this place, you should maybe even be able to skip straight to writing those answers out without really having to do all this work in your head. That multiple is just what you add every time. Okay, example 2 comes in standard form, 1 minus I for n equals 6. So we want to find the 6th roots of the complex number, which means we're going to have 6 final answers, which is okay because they follow that pattern and they shouldn't be too hard to get. First though, we have to think about converting this into trig form. So 1 and minus I would be down here. 1 and minus I, minus 1I, would be down here. So if you try to solve for r, you'd get the square root of 1 squared plus negative 1 squared, which would get you the square root of 2. Your tangent inverse would be of negative 1 over 1, which is going to give you a theta. It's either a 2nd quadrant or a 4th quadrant, and we know it's down in the 4th because tangent was negative. Okay, so we're going to do the inverse tan. That is one of the ratios on our special right triangles. It's a 45-degree reference angle in the fourth quadrant. We're going to use 315 degrees as that angle. Just like yesterday, however, since we're not going to give that as our final answer, we might as well go ahead and just call it something a little simpler. So instead of thinking about it as 315, let's think about it as that negative 45 degrees. Negative 45 degrees. The only hitch is if we look at our directions for our finding the roots, we're adding that multiple of 2 pi k, and 2 pi is in radians. And so we need to make sure that we think about that theta in radians. So we're going to think about negative pi over 4 as our number for this complex number. So our z here is really the square root of 2 cosine of negative pi over 4 plus I sine of negative pi over 4. And then we're trying to find the roots. So we take the 6th roots, which means I'm going to take the 6th root of the square root. Then I'm going to have cosine negative pi over 4 plus 2 pi k all over 6 this time, plus I sine of the same. Okay, I like to focus on that theta first and get it a common denominator so that finding these various angles becomes pretty quick. Well, let's make sure we don't forget to list out that our k is going to be from 0 to 5, one less. 0, 1, 2, 3, 4, 5. That should give us 6 total answers. Okay, finding that common denominator. If I flip and multiply, I'm going to get negative pi over 24 plus 1/6 pi k over 3. Find those a common denominator. I'm going to multiply by 8 here. And I'm going to get negative pi over 24 plus 8 pi k over 24. So now that I have my common denominator, I know my k is going to start with 0. 0 here means I'm adding none of those 8 pi's, which means my first angle is going to start out at negative pi over 24. So my first is going to be the 6th root of the square root. Let's just think about that really quickly here to see if we can write it any nicer. Hopefully you recall that roots can also be written as powers, and so the square root can be written as a 1/2 power. Hopefully this is coming back to you. The 6th root could be written as a 1/6 power, so I'm doing 1/2 to the 1/6. When you multiply those together, you're going to get 2 to the 1/12, or the 12th root of 2. If you could have arrived there on your own, that's good too. Okay, so we've got 12th root of 2 as our simplified 6th root of the square root. Then cosine of negative pi over 24 to start, plus I sine of negative pi over 24. Then we keep going. We're adding 8 this time. So this is a negative 1 pi, plus 8 is going to give me 7 pi over 24 as my next answer. Twelfth root of 2. That's my second answer. I'm going to have 6 total answers. I'm adding 8 every time. V3 is going to be the 12th root of 2, cosine 15 pi over 24, plus I sine of 15 pi over 24. V4, 12th root of 2, adding 8 to 15, I get 23 pi over 24. V5, 12th root of 2, add 8 again, I'm going to get 31 pi over 24. And the last but not least, 12th root of 2, add 8 again, 39 pi over 24. So I have 6 answers as my final answer for the 6th roots of the number. Final example is a little shorter. Cube roots, a little nicer. We should only have 3 total answers. And they gave it to us in trig form, so we should be able to hop straight into the formula. We're going to start off with the cube root of 27. Then we'd have cosine pi over 4 plus 2 pi k over 3 this time. And I sine of the same number, pi over 4 plus 2 pi k all over 3. Start off by solving for your theta, pi over 4 plus 2 pi k all over 3. If you flip and multiply, you're going to get pi over 12 plus 2 pi k over 3. Get a common denominator. It's going to get me pi over 12 plus 8 pi k all over 3. And those k's are going to go from 0 up to 2 for my 3 total answers. So the first one, when I plug in a 0, I'm going to get 1 pi over 12. So my first solution is going to be the cube root of 27, which, by the way, actually does cube root nicely to a 3. So 3 cosine pi over 12 plus I sine pi over 12. Second answer, still the cube root of 27 out front, 3 cosine. This time I'm adding 1 times that 8 pi, so I'm adding 8. My 1 pi over 12 plus 8 pi over 12 should give me a 9 pi over 12 as my second answer. If we're being picky, 9/12 reduces. They're both divisible by 3, so that's cosine 3 pi over 4 plus I sine 3 pi over 4. Okay, then our third and final answer, I add 8 again. 8 plus 9 is 17. That's definitely not going to reduce. 17 pi over 12 plus I sine of 17 pi over 12. So I get 3 total answers, V1, V2, V3, all using that formula. The trickiest part of any of these examples is that solving for theta, and I think taking the time to write it out and really think about those fractions, because we all still struggle with fractions, is probably the key component to getting these questions right. Taking your time, thinking about theta, getting yourself the common denominator, which I just realized I wrote out wrong when I actually got it. It should be a 12 up here. Getting yourself that common denominator, and then quickly being able to just add that multiple to come up with your answers.